This video, we're going to talk about acids and bases. And we're going to go through these notes, these pink notes. And I think I want to cover mostly this first part here. We might get into pH a little bit, we'll see. But to start, before we even get into acids and bases, we need to talk about water. That's where this whole story begins. Okay, so we have water here. Maybe I'll zoom in just a little bit. Yeah, why not? Okay, so we have water here. So we've got this beaker or cup full of water. There's all the little water molecules. Oops, this one is missing an oxygen. That'd be a weird hydrogen bubble. Okay, and we've got this model of water here. I actually, oh my gosh, I better put in those lone pairs, otherwise, I don't know, it'll just kill me. I can't bear to see it without them. So yes, we've got this model here. And this is what we believe learned about water so far, that water is 2 hydrogens, 1 oxygen. This is absolutely true, but in reality, it's a little bit more complicated. At any given moment, sometimes the water dissociates into ions. So we've kind of talked about that, like with dissolving. Essentially, the water kind of dissolves in itself. And what actually happens, just a little bit, doesn't happen all the time. It will dissolve to form the 2 ions, the hydrogen ion and the hydroxide ion. Now, this doesn't happen very often. It happens once in a while, and it's very temporary. In fact, we call this an equilibrium because this reaction is kind of going backwards and forwards sometimes, but most of the time the water sticks together. So if you have a glass of water, not very many of these molecules are going to be separated, but maybe a few of them are. Just a few. I meant to draw it the other way. Oops, that's the OH and that's the H plus. Okay. And it could be any one of these water molecules. Let's just cross that one out. Write it in so we can see it a little bit better. Okay, there we go. So that little one just split and immediately they're going to come right back together. But then another one will dissociate and come right back together. And this process is happening all the time. And this is where we get the idea behind acids and bases. Acids and bases have to do with hydrogen ions and water and kind of hydroxide ions, but mostly hydrogen ions and water. So if we take a look at this process, we will find that if you have pure water at 25 degrees Celsius, water at 25 degrees Celsius, this process happens. Let me double check this because I have the thing here. Let's make sure I got this correct. Sorry, 1 second here. Yeah, this process happens so that the concentration of the H plus ions, which is what these little brackets mean, which is also equal to the concentration of OH ions at any given moment for pure water, is equal to 1.0 times 10 to the negative 7th molarity. So it's a pretty low molarity, right? But that's the concentration of the hydrogen ions. So very infrequently. So of this water, most of the time the water's sticking together as a liquid, but sometimes it's splitting apart into these ions. Actually, I can write that in. It's a liquid, that's aqueous, and that's aqueous. Okay. So this number is going to come back to us. It'll be sort of important, the fact that it's 1.0 times 10 to the negative 7th. That's actually very important. But this happens very infrequently. So acids and bases are defined in comparison to water. Acids have higher concentrations of H plus. And bases have lower concentrations of H plus and higher concentrations of OH. So let's talk about what an acid is and what a base is and how this whole thing works. Back to the notes here. So an acid is any substance that donates an H plus when it is dissolved in water. And a base is something that accepts H plus. H pluses are also known as hydrogen ions, and we can also refer to them as protons, frankly. So let's look at a few examples. We'll look at a couple examples of acids and bases. I have a whole list here. All right. Usually what I like to do is I like to say that these things are reacting in water. So let's have these all reacting with water. It'll just be easier if we do that. Let's see what the product is. This should all make sense. Draw some arrows in here. Okay. So in this particular case, when H plus dissolves, you're going to end up with two separate ions. And you're going to end up with the H ion, the H plus ion, and the Cl minus ion. Those are the two ions when it dissolves. And what happens here is this H plus gets donated to the water. And so we're going to end up with H3O plus and the chlorine ion. Actually, I'm going to draw the H3O plus in blue. I changed my mind. Not that you can tell much the difference, okay? H3O plus is basically the same thing as H plus. So another way of writing this is, we'll simplify just to help things out a little. I can never decide if I'm going to do the AP Chem version of the explanation or the Gen Chem version. Either way, there's two different ways of looking at it. Same thing. Okay. The HCl, when it dissolves, it's going to form these two ions. And what we've done here, as you can see, we've added H pluses. So if we were to go back to our example of water, if we dissolve this, the water itself is creating a small amount of H plus because it dissociates a little bit. But if we add HCl, the hydrogen is adding a lot more. The hydrogen from the hydrogen chloride from the HCl. So we're going to end up with a much higher concentration of hydrogen ions. So this is an acid. HCl is definitely an acid. Okay. All right, let's check it out for H2SO4. So for this one, we actually have two hydrogen ions. So we're going to end up needing two waters. Let me write this in a more simplified way, and then we'll go back to the fancy way, just because I can't help myself. I love being fancy. I love adding it to water. Okay. H2SO4, so we're going to end up with two hydrogen ions and one sulfate ion. That's a 2- charge. Okay. So once again, we are adding when this dissolves in water, it's going to create more hydrogen ions in the solution, which means it is an acid. Definitely an acid. Okay. If we want to think about this another way, we could say that those hydrogen ions, so like what happens is if you just have a free floating hydrogen ion, it tends to just glom on and stick to water. So you just end up with H3O plus. It's called a hydronium ion, but it's the exact same idea, that you end up with an H3O plus, and you're also going to end up with an SO4 2-. So you're going to have two of these. Yeah, they have some places to go. Same idea. Okay, so it's an acid. All right. How are we feeling about that? Hopefully good. You guys can't answer, so hopefully that makes sense. Okay. There is, this is another one. Let me see. I'm actually I want to rewrite this one at the very bottom. Sorry. Let's just scratch that one out for right now. So these are acids. Now, what about something like NaOH or BaOH or these hydroxides? So when these dissociate, I'll write this out a little, again, the more simple way, and we'll come back to the more complicated, fun way. When these separate, we end up with sodium. Sorry, the bells. All right, so we have sodium hydroxide, so we end up with a sodium and a hydroxide ion. But that doesn't really have anything to do with H plus. So how do we know what happens next? Well, here's what happens next. Hydroxide is going to interact with one of the waters from the solution, and it's going to take away one of its hydrogens. And yeah, it's basically stealing hydrogen from water. And the result, of course, is just going to be like this passing of this hydrogen back and forth. So you're just going to end up with like a different hydroxide and a slightly different water combination. So it ends up really being this strange way of thinking about it. But when we say like that it accepts a proton, or a hydrogen, it's because it's really stealing one of the hydrogens from another water as soon as you add that hydroxide. So that's like the process of like how this happens. So in this case, yeah, we're stealing that hydrogen. So we're going to end up with some sodium ions, and yeah, we'll have a water. So kind of stays the same there, and also hydroxide. Kind of a weird way of writing this now that I think about it, but yeah, kind of helps get the idea across of what's going on here. Okay. All right, so that's bases. There's another base here. If we do the same thing, it's going to have to steal 2 hydrogens. So we kind of need like 2 of those. You know, I'm just going to write it without the water this time. I think it'll be easier, and you'll get the whole picture. So it can get a little bit more complicated than this, but generally speaking, if you see an OH, it's a base. If you see an H+ at the beginning, it's an acid, right? So in fact, I have a whole list here. These are a list of strong acids and strong bases, which we'll talk about in a second, but there's a whole list right there. Okay, there are a few more things I want to talk about here. There is polyprotic acids, or acids with more than one H+. So a good example of that would be H2SO4, like I just showed you here, because it has 2 hydrogens that it can give. So it has more than one, polyprotic. Amphoteric is something that's good. Okay, so this is a fun one. Maybe this will be good. Okay, this is, I'm going to talk about this particular delightful polyatomic ion. This is HCO3. Did I draw? No. Anyway, okay, sorry. HCO3 negative. This is a polyatomic ion. It's a hydrogen carbonate. This is actually what's in your blood that helps regulate pH, which is really important. So if this interacts with water, there's actually 2 possibilities. Right. It's all out for you. Okay, so one possibility is that it is an acid, and one possibility is that it is a base. Oh yeah, I forgot to label these both as bases. Okay. So this is what you'll see by accepting or donating hydrogens. I think it becomes more obvious here. So in this case, because it's a -1 charge, it could take a +1. Like it can grab another hydrogen, because hydrogens are +1 charge, and actually that would neutralize it. So if it were to act as an acid, it would take one of these hydrogens and just steal it. So we would end up with H2CO3. I'm sorry, that's when it's acting as a base. Sorry, bases accept them. I'm so sorry. Let's switch that around since I already did it this way. Sorry, acids donate, bases accept. Sorry about that. Hopefully I caught it pretty quickly. So in one case, it's going to nab a hydrogen off of water to become H2CO3, which is neutral. And in another case, and we actually should have drawn that in red for consistency. And then because that water has lost a hydrogen, it is now going to be OH negative. So we have basically, added OHs, which makes it a base. The other option is for it to be an acid, which is a proton donor. It has a proton, it has an H+, it becomes an H+ donor, hydrogen ion donor. If it does that, we're going to end up with CO3 2- as the new polyatomic ion, the carbonate ion, and because we've added a hydrogen to this water, we've donated it, we end up with H3O plus. So another way of thinking about this one is just you've got HCO3 negative, and it's going to create a hydrogen ion and a CO3 negative, 2 negative ion. Okay, so either way, you have added hydrogens. So it's a hydrogen acceptor. So the solution now has more hydrogens. Okay, this is something that we call amphoteric, this example. If you think of it, it's kind of similar to ambidextrous, it's a similar idea. It means that it can be either an acid or a base. So yeah, I don't exactly know where this comes from. But amphi, like ambi, similar, like ambidextrous means you can use both hands. Amphoteric, same idea. It can act as both an acid or a base. Okay. So that's some of the essentials. I cannot say the word basic during this unit. That's some of the essentials of acids and bases. I can tell you this, a strong acid is any acid or base, a strong acid or a strong base. It has nothing to do with how powerful it is. It's how much it dissociates. These are all examples of ions that dissociate completely. So like HClO or HCl or H2SO4, those are both strong acids. Strong bases, NaOH and BaO2 are also strong. Weak acids and weak bases are acids and bases that do not dissociate completely, which is basically a good example. Sorry, I can't use the word. Water. Water is a great example of this. It is actually a weak acid and it's also a weak base because it breaks down and dissociates, but most of the time it stays in its original form. So I can give you an example of a weak acid. A weak acid, a good one is, so switch into a regular pen for this, is vinegar. Vinegar is made up of, what makes it vinegar is acetic acid, which is hydrogen acetate, which is HC2H3O2. Okay. And most of the time, this molecule is just dissolved in water, but it's like you can think of it kind of like it's a covalent molecule. It sticks together like sugar. But acids and bases are weird because they're sort of covalent, but they're also sort of ionic. So they will sometimes be more ionic and like dissociate into their two separate ions. So that is true with acetic acid. Sometimes it breaks apart into its two ions. But most of the time it sticks together. So that's how you know that something is weak versus strong. Weak acids, we're not going to worry about those very much. Just know that they exist. AP Chem, it's a huge thing. All of like Unit 8. Unit 8 is all about weak acids and weak bases. It's really fun. Okay, so that's some essentials about acids and bases. Let's talk about reactions. So acids and bases react together. A classic example that all know is baking soda and vinegar. So vinegar is a weak acid. Baking soda is actually a weak base. So when those two react, it bubbles up, creates a whole bunch of, it actually creates a whole bunch of carbon dioxide gas, which is what bubbles up. Is it carbon dioxide or is it oxygen? It's one of the two. I can't remember at the moment. We have to write down the reaction. But anyways, when you have an acid and a base reaction, they tend to neutralize each other. It always has to have, these reactions always have one of each. And let's give you an example then. So this is a great classic example for us here. Actually, we just said the other one. Let me write it down just for funsies. HC2H3O2 plus bicarbonate. Sorry about this, y'all. Gotta write it down before I forget. And then we end up with it's H2. Water and CO2. I think are the two products. Okay. So yeah, so this is actually the acid, this is vinegar and that's baking soda. And so what you end up here is we have an acid, because we know that because of the H plus. And we have a base. And it's a little hard to know that it's a base, but it's because it accepts it can accept the hydrogen from the acid. And you end up with kind of this funky reaction. You end up creating, I think, some water and carbon dioxide. It's actually sort of complicated. Like the first step is that you create you end up with the hydrogen from here kind of reacting from this H2CO3. But that immediately like breaks down. And I'm pretty sure it's into water and carbon dioxide gas. I could be wrong though about this one. It might be something else. I don't remember at the moment, but I think this is what actually happens. Anyway, I don't think that was as helpful as I was hoping. All right, moving on. Let's go back to this example then. So this one is much more clear. So this one, we have an acid and a base are reacting. The HCl is the acid because it has a H in the front. So we know that it could give a hydrogen. It has a hydrogen to give. So that's an acid. And NaOH, anything with an OH at the end is pretty much a base. You know, it's a little funky knowing that this is a base because it doesn't look like it is one. Kind of looks like an acid. It's hard to tell. But the examples I'll give you will be pretty obvious. So when you see OH, know it's a base. All right. So this is a reaction. The products are sodium chloride and water. And we call this also a neutralization reaction because you are kind of neutralizing the acid. You're getting rid of the acid and the base so that it's just all to zero, which we'll have to talk about the pH scale, which we didn't mention before, but maybe the next video. One thing to note about this is that you do have this concept of conjugate acids and conjugate bases. So it's essentially like what happens they kind of form these pairs. Hold on, let me just see if I've got a better example of it. I just realized I don't love this example. Let's see what we can find. We've got a couple at a times in here. We have to write these down. Oh, no, it's easy. Okay, this is totally fine. Awesome. So the conjugate acid and the conjugate. Okay, so a conjugate acid and conjugate base are these pairs. So it's like when a base reacts with an acid, it's going to take a hydrogen on. So when it takes that hydrogen on, it's going to form an acid because it's something that if it took a hydrogen, it would then be capable of giving one away. The same thing is true of the acid. Once it's given away its hydrogen, like what does it look like? So in this case, we have our acid here. So the question is, what does this become after it's given up its hydrogen? It's going to form what we call a conjugate base. It's the base that is connected to that acid. So after this hydrogen, after this hydrochloric acid, HCl, has given up its hydrogen, what's left is the chlorine. And so we have to kind of find the species that has the chlorine in it, which in this case is the NaCl. So this is the conjugate base because it kind of has this, like, it's a little invisible, but it's really the Cl negative. Because it has a negative, it could take on a hydrogen. So it could be like a base. So these are a pair. So we call this the acid conjugate base pair. So in this case, it's HCl and NaCl, the acid and its conjugate base. The opposite is a conjugate acid. So what happens after this sodium hydroxide takes on a hydrogen from this hydrochloric acid? Well, it's really just going to form water. The sodium is kind of, we don't want to include the sodium. It's really more about the chlorine there. So the sodium kind of, it's like this dissolves. Yeah, that's going to make this more complicated, but that's okay. It's okay. We'll do the best we can. That is our conjugate acid. So these are a pair. So really it's the hydroxide and the water are the conjugate, the base and its conjugate acid. So that's sort of the concept behind this. There's a couple better examples in the packet that I think we can go through. All right. I think that, should we go through a little bit more? You know, let's go through a few more things and we're going to come, I'll divide the videos a little differently than I originally thought. So let's talk about the pH scale. So I want to go back. Do I have that picture? I do. Okay. This is the pH scale, and it is a way of measuring whether something's an acid or a base. It is, pH has a scale from 0 to 14. But the 0 to 14, it's a little confusing what this actually means. pH is actually measured, is actually based off of the concentration of hydrogen ions in a solution. And it's not a direct connection. It is actually a calculation, which I did not put on here. And that was a big mistake. I should have done that. Okay, so the pH is a number that is based off of the hydrogen ion concentration, but first we have to do the negative log of it. So I want to go back to this example with water so we can talk about it. Water is considered neutral and it has a pH of 7, pure water. It's listed right there in this kind of weird drawing. that diagram is not very clear. If you remember from what we said earlier, 20 minutes ago or whatever it was, that the hydrogen ion concentration of water is 1.0 times 10 to the negative 7th molar. If we take that and we do our little equation here, our little calculation here, we take the negative log of 1.0 times 10 to the negative 7th molar. I'm going to show you how to do this. You're going to need your calculator for this. You need to find the log button, which is this one right here, and you need to make sure to make it a negative number. So the negative, it's like the logarithm times -1. Maybe we'll just do the log first. That might be kind of fun. So we need to do the log of this number. 1.0 times 10 to the negative 7. Okay. It's really easier. It's much easier to find that EE button. It's going to make your life a lot easier. And you get -7, and let's just times that times -1, and you get 7. So that's why we use the pH scale. We use a log scale because if we had to just write these numbers are all very small. Even the biggest numbers are not that big. And some of the numbers that you're going to end up with are very, very, very tiny. It would be really inconvenient to have to write this every single time. And most people are not very good at scientific notation to begin with, like your average person who has to like do pool pH or, chlorine levels and all that kind of stuff in pools and other reasons that we use pH. So it's so much easier just to have a number, a whole number that's just easy to work with. The way that this really works is that -7 is why that this is a 7. So negative log, you end up with that. So that's kind of how this works. So this is why water has a pH of 7. It's because of this constant at 25 degrees Celsius, the dissociation of water. Okay. So acids are going to have a higher concentration. So let's just say we have an acid, and let's just say it's hydrochloric, and we say that it has an H+ concentration of, let's say 1 times 10 to the -3 molarity. That's higher than 1 times 10 to the -7th. Well, what's its pH? Well, we do the negative log of 1 times 10 to the -3. Yeah, that's what I said. And we end up with 3. So the pH is 3. What if we have H2SO4 and I tell you that the hydrogen ion concentration is, let's make something weird, 3.4 times 10 to the -4th molarity. I got to get lights back on. All right, so we can do that math. It's gonna be a little less obvious, but it should be something like 4, maybe a little higher than 4, maybe or a little lower than 4. So the negative log of 3.4 times 10 to the negative 4th. And that's 3.47, it looks like, is the pH. Okay, so that's kind of how that works. So in this case, bigger numbers, like this number is actually a bigger number than this one, have a lower pH. So low numbers, like a pH of 0, is very, very acidic, very high hydrogen ion concentration. If we have a base, bases are going to have very low hydrogen ion concentrations because we've got all this hydroxide that's sucking up those hydrogen ions and pulling them out of the solution. So this one might have a hydrogen ion concentration, let's say of maybe 7.1 times 10 to the negative, I don't know, like 10 molarity. That's pretty low. That's a very small number. So if we do the negative log of 7.1 times 10 to the negative 10th, we get, yeah, like 9.15, which we'll see is a base. 9.15 is definitely in the base range. So small numbers mean big pHs, means basic versus acidic. And that's where it all comes from. Hopefully that makes some sense. So when you look at a pH scale, you can actually calculate this stuff pretty easily in using that. So again, this is the dividing point, is the hydrogen ion concentration. And those are the two formulas that you might need to solve. We're going to do more calculations involving hydrogen ion and pH constant math, but that's just the essentials. God, I cannot say the word basic that you'll need to do these. All right. So let's take a look at the packet, because I think at this point you can actually do quite a bit. This is page 1 of the packet. There's a few things I'm going to cross out for you all. I'm going to say don't bother with this. Yeah, don't bother with number 1. You don't need 4 or 5. The rest of these look pretty good. So yeah, so these ones, pH of 13, for example, a solution with a pH of 13 is not acidic, it's actually basic, so that's false. A solution with a pH of 13 would in fact be basic, so that is true. Pretty cool. In this case, we can look to see if the water is acting as a base or an acid. So we have to think, like, is it accepting a hydrogen or is it giving away a hydrogen? In this case, for A, it looks like the water is taking this hydrogen group and it's turning into H3O plus. So if it's accepting a hydrogen, it is acting as a base. In this case, it looks like the water is giving a hydrogen to SO3, and then that SO3 is like that. So it looks like in this case, it's acting as an acid because it's giving up a hydrogen instead of accepting it, hydrogen ion. Okay. So in this case, same thing, circled the acid and the base. So in this case, we have, let's pick out a fun one. This one's a good one. So it looks like we've got H2PO4 negative and CO3. It looks like this phosphate-based ion is giving up a hydrogen. So that means it's an acid. So I'm just going to put acid above it, A for acid. And this one is accepting, the CO3 is accepting a proton, so that means it's a base. Okay. And if we want to go crazy, we could talk about conjugate acids and conjugate bases, but we don't have to. So we can talk about that here. We're talking here about conjugate acids and conjugate bases. Here we have, if we're saying that this is an acid, so water's an acid, what would it look like as a base? Well, after it's given up a hydrogen, it's going to be O minus. We have an acid here. What happens after it gives up a hydrogen to turn it into a base? It's going to be H, SO4, and it's going to be a minus charge. Same thing here. We've got a base. What happens after it's taken on a hydrogen? It's going to be H3O plus. And what happens if HPO4 2 minus has taken on, has been a base, it's grabbed a hydrogen? It's going to be H2PO4 minus. Okay. So page 1 is just kind of some simple stuff. I'll leave a few things for you to work on, but hopefully that helps. I would say you can also absolutely handle page 2. It's got some stuff about definitions. It's got a little bit of this kind of pH thing there, which is sort of fun. Oh, you can skip buffers. We don't need to know what a buffer is. Don't do that. Yeah, that one should all be okay. Let me just make sure all this makes sense. I think it does. This one you don't have to bother with. It's a little more, you can try it, but it's not too bad. Electrolytes, we've kind of already done that, so that's not too horrible. It was last unit. And I also think you can do page 3 about this acid base pairs. This is going to take a little bit more practice, I bet. But maybe I will, yeah, let's do an example for this. Yeah. So let's take a look. I'm going to pick a random one. I like number 6. So we have to figure out what's an acid and what's a base. I'm going to grab different colors here. So it looks like here, this ammonia is, if we follow it, it looks like it gave up a hydrogen. So this must be an acid. And therefore, that is the conjugate base. And these two are sort of paired off together. And this one looks like it's accepting a hydrogen, so it must be a base. Sorry, wrong color. And this would be its conjugate acid. So those are the 2 pairs. So that's kind of the idea behind it. It's a weird concept, but you know, once you get used to it, it sort of makes sense. So like, where's the hydrogen going? Okay. So you might need to do a little bit more practice on those, but this is definitely doable. And then I think, man, I really want you to learn about conjugate acids and bases because page 4 is the same thing. So more practice. I'll have to go through and I'll do some more, some answer keys. And then page 5 is more of the same kind of stuff. It's conjugate acid base pairs. So yeah, this is definitely going to be a lot of practice on that. Page 6, definitely we're going to do on the next video. So anyway, there's some stuff for you to look at. Hopefully you found it kind of interesting. Acids and bases, it's very useful. It's good stuff to know. And especially for AP chemistry, it comes in really handy. So we'll come back and we'll talk more about the calculations. And then there's one more topic in acids and bases after that. So I'll see you next time. Thanks, y'all.